Hello everyone again. So now I want to extend the discussion about multiple pipe systems, and now I want to introduce the parallel pipes. So as you remember, the pipe systems are similar to electrical circuits, and we looked and we saw an example of a series pipe and how to deal with that. And now I want to introduce parallel pipes similar to parallel circuits where we have parallel resistances. We can have also parallel pipes where from one reservoir we can have multiple pipes that go to the second reservoir. And so now we want to see what are the governing equations for this system of multiple pipe systems. Okay, so again, the governing equations are the same, but I want to look particularly at these parallel pipes and see how we can tackle this type of problems. So again, you start with writing the energy equation. And one thing that we can assume for these type of systems is that the head loss experienced between point A and point B is the same, independent of the path the fluid takes. So either it goes from here or here, so it's either it goes from 1 or it goes from 2 or it goes from pipe 3, so from any of them, so the head loss that it's gonna experience up to here is gonna be the same. Okay, so this is the first thing we can say about parallel pipes, and this is shown here. HL1 from pipe 1, the head loss from pipe 1 equals to head loss from pipe 2 equals to head loss from pipe 3. So this is the first thing. And then the second thing that we can say is the mass conservation. So this is the mass conservation. And what we can say is that the total flow rate, mass flow rate or volume flow rate that goes from reservoir A to reservoir B equals to the sum of the flow rates from each pipe. So Q total is going to be Q1 plus Q2 plus Q3. So this seems kind of like straightforward to understand, and that is how we deal with parallel pipes, and these are the two governing equations we use to tackle parallel pipes. So now let's solve a simple example for these parallel pipe systems to better understand what is their difference. So we have two pipes that are connected in parallel between two reservoirs that have difference in levels of 3.5 meter. Okay, so we have like one reservoir here and then one reservoir here, and these have there are two pipes that are connected to these, and this is reservoir 1, say, and this is reservoir 2, and the difference between their levels is 3.5 meter. Okay, so this distance here is 3.5 meter. Okay, so this is kind of the problem here. The length, the diameter and friction factor are 2,400, 1.2 meter, and 0.026 for the first pipe. So this is the first pipe, say, and this is the second pipe. And 2,400, so they are the same length, 1 meter but with different diameter, 1 meter, and 0.019 for the second pipe. Okay, calculate the total discharge between the two reservoirs. Okay. So we need to find what is the total discharge, the flow rate from here to here, reservoir 1 to reservoir 2. So first, we have to calculate the head losses in this system. So the head loss, let's say we only have major head loss here, because in the problem there is no indication about any minor head loss, like any additional component in the system that can be like an elbow, or I don't know, like a valve or a faucet or anything. So for the major head loss, which is due to the friction, we have F multiplied by L over D. D is the diameter of the pipe, multiplied by V square over 2G. So I can put 2G here, and instead of V, write Q over A, which is Q over PD square over 4. So I'm going to get something like this, right? So instead of V, I just wrote Q over A, and A is the area of a circle, which is PD square over 4. So I can write it F multiplied by L over 2GD. So 2G, I brought it from here. And then instead of V square, I write 4Q over PD square to power 2. Okay. So this is just rewriting the equations to kind of mimic what we have in the problem. Okay, and this equals to 8 times F L Q square over P square G D to the power of 5. So here we have D, and we have D here, 1D, and we have D to the power 4 here. So it's going to be D to the power 5. Okay, so now let's put the numbers in. So HL is 8 times F1 for the first pipe, F1 L Q1 square over P square times G times D1 to the power 5 equals to, and the other thing that we know is what? We know that the head loss from pipe 1 should equal to pipe 2, because we are in a parallel pipe system, right? So here, right, we are in a parallel pipe system, so a head loss for each of these should equal to each other. So I just write it for both pipes, pipe 1 and pipe 2. The head loss should be the same. So this one equals to 8 times F2 times L times Q2 square over pi 2 G D2 to the power 5, where D is the diameter of the pipe. Okay, so now I write the energy equation. So this is energy equation between point reservoir 1 and reservoir 2. So between reservoir 1 and reservoir 2, the difference in the elevation is 3.5, so that I write it in the left, and the pressure here from 1 and 2, they are in the vicinity of atmosphere, so I can just assume that the pressure is 0 if I am measuring from the gauge pressure, and also V for both reservoirs is about 0, because they are very big reservoirs. Okay, so I am only left with 3.5, which is the elevation difference and the head loss in the system. So let's first write it for the first pipe. So it's going to be 8 F1 L Q1 square over pi 2 G D1 to the power of 5. And I just substitute all the numbers here. 8 multiplied by F1. So F1 here is 0.2026. So I just write it down here. Multiplied by 2,400, which is the length of the first pipe. And then Q1 square over pi squared times 9.81, which is G, multiplied by D1, which is 1.2 to the power of 5. Okay, so now I have the only unknown here is Q1, and so I can find Q1, which is very easy. It's gonna be 1.29 meter cube per second. So I found the discharge between 1 and 2 for pipe 1. So we can do the same thing for pipe 2, exactly the same thing, but just change the numbers here. So instead of F2, I put the friction factor from the second pipe, which is 0.019. And then the length here is the same, is 2400 Q2 square over pi squared times 9.81 times 1 meter, which is for the second pipe. And then I am gonna get, if I solve this equation, the only unknown here is Q2, so I'm gonna get Q2, which is gonna be 0.96 meter cube per second. So now I have the discharge for both pipes, pipe 1 and pipe 2, and now it's very easy. In order to find the total discharge, the only thing that I need to do is to sum the discharge from pipe 1 and 2. So here you saw that for a parallel pipe, we need to sum the discharges in order to get the total discharge or total mass flux or volume flow rate in a flow. Okay, so this is the total volume flow rate in between reservoir 1 and 2, reservoir 1 and 2, which is going to be the sum of two flow rates, Q1 plus Q2, which is going to be 1.29 plus 0.96 equals to 2.25 meter cube per second. So this is going to be the final solution here, the final answer here. Okay, so this was kind of a simple example. This was type 1 problem, if you remember. So for type 1 problems, yeah, so if you remember, this was a problem where we have the pipe diameter, and we have this was type 2 problem. So we have pipe diameter here, and we have delta P, right? We also have delta P, and then, so this is type 2, and then we want to find what is Q. What is the flow rate? Okay, so this one we were able to solve it by converting everything to the flow rate, and it was a relatively simple example. Okay, so now let's start and talk about the third type of multiple pipe systems, and that is what is called a loop. So as you can see here, a loop is where we have branching in a pipe flow system. So we have like connected pipes, and suddenly a pipe branches into two or more pipes. So this is what we call as a loop. Okay, so we have an entering flow rate and two exiting flow rate at Q2 and Q3. So the first pipe has D1, the second D2, and third has a pipe diameter of D3. So let's see what are the governing equations for this type of systems. So for these type of systems, we can say, again, similar to parallel pipe systems, we can say Q1, the entering mass flow because of conservation of mass, should equal to the sum of Q2, the exiting outflow from the system, Q2 plus Q3. And the other thing that we can say is HL, because these two are kind of parallel with each other, the system is going to experience the same head loss from this point to, say, this point, right? So the HL2, the head loss inside pipe 2 should equal to the head loss inside pipe 3. And the other thing we have is, because this is kind of a combination of a parallel and a series, and here we have like this one, which with these two is kind of consist kind of a series pipe system. So when we write the energy equation, which is shown here, we are going to consider summing the head losses between 1 and 2 or 1 and 3. So when we write the energy equations, they are going to look something like this. So either we are going to go from like here, let's say pipe 1, and then go to pipe 2. So we are going to choose this direction, and then that is going to give us this PA over gamma plus VA square over 2G if we consider the energy equation between A and B. Plus ZA equals to PB plus VB square plus HL1, so the head loss from here, plus HL2. Or, so these are gonna, we are gonna sum these two, right? You're gonna sum both of HL1 and HL2 because you're going through this direction. Or we can write it the other way. We can go from this one, and you know that HL2 equals to HL3, right? So we can go from the other direction and write it as PA over gamma plus VA square over 2G plus ZA equals to PB over gamma plus VB square over 2G plus HL1 plus HL3. So we are going to go from this one, and these two equal, and they are equal to each other, so we are going to get the same answer. So this is when you want to write the energy equation between A and B. So this is this loop is kind of a combination of a series and a parallel system. Okay. So now let's go to the fourth and last multiple pipe system that we are going to describe in this session, and that is what we call as three-reservoir system. So the three-reservoir systems are three reservoirs that are connected to each other at known elevations, right? So we know the elevations of these three reservoirs, and they are connected to each other, and each of them have are connected with different type of pipes. So this one can have like pipe 1 with L1 and D1. This one can have pipe 2 with L2 and D2, and this one is pipe 3, L3 and D3. And we have like a loop here, like a branching, and we have different components like minor head losses in the system. So this is kind of like a combination of all the things, most of the things that we learned in this session. So now let's see how to tackle this kind of problems, these kind of systems. So in this type of problems, typically we know the properties of the pipes, like we know their roughness, or even we know sometimes their diameter. We usually know their length, and So these are the things that we know in these kind of problems. But one of the things that are that is not obvious in these type of problems is the flow direction. So we don't know actually what is the direction of the flow, and this should be determined. So we should determine what is the flow direction. And to elaborate on that, for example, say here the flow comes from A, so goes out of A and reaches here to this branching. So we don't know whether the flow is gonna go up, is gonna go into the reservoir B, or is gonna come from reservoir B into this branching system, right? So we don't know this, and say here we know that it goes down, but this direction we don't know. So it really depends on the difference in the elevation and also the pipe properties, like how much kind of flow rate they might have, and what is the elevation difference, and also the head losses in the system, whether we have like a big head loss here or a small head loss is going to really affect here, or the same here. If you have a big loss in pipe 2 or a small head loss, the flow direction can change. It can go whether inside the reservoir B, or it can even go out of that, right? So here this is what one thing that we don't know, and in the course of solving the problem, we have to kind of determine and find out what is the direction of the flow. And typically what we do is that we assume at the beginning, we assume a flow direction that seems more logical or more reasonable to us, and then we solve, we go through the governing equations, which are the mass conservation equation, the flow rates, and also the energy equations. And after going through those, if they all make sense, and if they all, we can get the correct answer that satisfies all the equations, then that was the correct direction that we initially assumed. However, if we get to a point where we see that these solutions do not work, and there is it is not possible to have such solution for any solution to satisfy both energy equation and mass conservation, we find out that the assumed direction is wrong. So we have to change our direction that we assumed initially and solve for the problem again with the new direction. So in that sense, this is also kind of a trial and error kind of approach where we have to take in order to solve this type of problems. Okay. So the next thing that I'm going to do is to solve an example for these three reservoir multiple pipe systems. And due to the interest of time, and because this example is kind of difficult and needs a lot of trial and errors, I will just introduce the problem here so you get familiar with that, and next time we are gonna solve this problem. So as you can see, we have a three reservoir pipe system, A, B, and C. And then we have a branched a loop here where we have a branched pipe from 1 to 2 and 3. And then the problem wants us to find the flow rate into or out of each reservoir, right? So we want to see what is QA, like here, QB here, and QC here. So we want to find whether the flow first is going to go into or out of each reservoir, and what is going to be the value of that flow rate. So some of the things are given here. For example, friction factor for all the pipes are given to simplify our life, so we don't have to go to the Moody diagram and have the go through the like know the Reynolds number and other things. So this is something that is given for to us. We know the diameter of the pipes, we know their lengths, so these are the other things that is given to us. And we also know that we don't have, we can assume that we don't have any minor losses, like we don't have any additional component in the system, so we can only account for major losses, right? So we know this, and also we know the elevation of each reservoir. So elevation of A is 100 foot, this one is 20 foot, and the elevation of this one is 0 foot. Okay, so with all this information that is given here, we want to find what is the flow rate into or out of each reservoir. Okay, so I'm going to solve this example in the next session, and what we are going to do, we are going to write continuity equation, which is like that mass conservation equation, and because the flow rates are, the diameters are the same, we are going to get a relation for the velocity, and then we are going to also write the energy equation from A to C, and also from B to C, so these two, and then we are going to have three equations, and we want to find, we have three unknowns, which are the velocity in each pipe, and then we will find what are the velocities in each pipe through some kind of trial and error and some assumptions about the flow direction. Okay, everyone, thank you very much for listening, and we will continue the course in the next session.